Okay, good morning. And as usual, let's start with a summary of week 12. So last week we talked about, we're motivated why we're interested in studying polymers by taking an account of the filaments in the cell. Most notably, you should remember DNA, which is a kind of one of the flexible polymers compared to the polymers of the cytoskeleton, namely actin, intermediate filaments, and microtubules. So these are cytoskeleton, and typically considered semi-flexible, although there's basically over all of these kind of a gradient in stiffness that goes like that. So microtubules are the stiffest, microtubules, and DNA is the most flexible. And then we learned how to describe them by first of all introducing the freely jointed chain model. Which is a model for flexible polymers. And here there's no energy cost associated with any configuration of a polymer. So we really just describe the state by its entropic component, which is by the state being defined by the tangent vectors connecting along the bond connecting the two segments I and I+1, which we consider monomers. Similarly to the one examples that we had, there could be entire compounds. Most strikingly, the state is more or less given already by the tangent correlations, which is there's no correlation between them at all because they're statistically independent, except for if we're looking at the self-correlation. And this then sets the probability distribution of the polymer state to be 1/4πb², and then the product over all independent tangents, which are constrained to be equal to the length of the bond B. So this constraint says that this distance is always B, and it's something that only becomes apparent if I stretch. If I take the two ends of a polymer and I want to and apply force on it and I stretch it, then eventually I will realize that there is this constraint that I can only stretch the polymer to a length of NB. And indeed, the most important observable to characterize these polymer states that highly crumpled up typically are the end-to-end distance vectors, which is defined by xn minus x naught, or equivalently the sum over all tangents. And for this one, we found this universal law that the end-to-end distance vector is equal to NB². So scaling the square scales linearly in n, and the length scale is a length scale of the bond length. Indeed, the end-to-end distance vector follows a Gaussian distribution in 3D. Given by this Gaussian. Then we calculated the free energy of the polymer and found it to be a 3 kBt over NB squared R squared, and realized that this is exactly the form of a Hookean spring, where we now here identify a spring constant K, which is entirely entropic in nature. And so how do we see that there's a very different physics driving this spring constant? Well, we see that this spring constant becomes bigger if we increase the temperature. And that's contrary to our expectations. If we take a solid and we heat it, then it becomes softer and easier to stretch. For these entropic spring, we derive the force extension relationship to be minus 3 kBt and B squared Rx, which is the one for small forces. So this was the entropic spring. And notably, this relationship could also follow from the blob picture. Where we coarse grain the polymer in this stretching by realizing that what the forces are doing is they're stretching out the polymer. So we consider the polymer as strengths of individual blobs of length psi. And now here, the balance of the force lining up these individual elements individually has to be equal to the thermal energy. And similarly, because now the end-to-end distance is n with the number of segments in the fold chain over n, the number of blobs times psi, and also the individual blob scaling with this universal law, where is it here, with n being the amount of monomers per blob, we can put this together and find also this relationship that n over n psi is then equal to b squared n over kBt f. So recovering this result as proportionality, there's a factor missing. Also, just to add, this is the result for small forces. We also went for the exact calculation to find that for large forces, we get the following relationship, that as we stretch the polymer to the length of the entire polymer n times v, then this force diverges. So eventually I'm acting against the the segment, the stiff bonds. So that was this free jointed chain model, and then we generalized this setup to the Gaussian chain, which is kind of a coarse graining approach of the free jointed chain, where essentially what we're doing is we're replacing these stiff bonds that are sort of, make math more complicated because they define this constraint as entropic springs itself. So this does not affect the large scale behavior of the spring. On spatial scale is much bigger than the individual interbond distance, bond distance. So we're going from what's in the really jointed chain, a bead rod model, to a bead spring. The spring refers to the entropic spring, which means that each bond becomes now a Gaussian subpolymer. And with that in mind, we can then write down the propagator of the end-to-end distance of this Gaussian chain as a path integral formulation. Okay. We're integrating over all configurations of the path that it may take from the given end vectors, which has this, the Gaussian from the probability distribution here propagates down here. And so we can also identify this path integral formulation as an integral, with this being an effective Hamiltonian. And indeed, this is then called the so-called Edwards Hamiltonian, being defined as epsilon L 0 to 1 d sigma dr d sigma, where what we are integrating over is the configurations of the line and space. And so then we identify that this prefactor epsilon here is an entropic line tension. So this is integral. And then at the very end, we started with the scattering function as to derive an observable that we can compare to experimental data. And here we found that the scattering function, which is the Fourier component, Fourier space of the density, is given by the double sum of, and this is in Fourier space, J minus I. And so today we will continue to quickly finish up on the scattering function, and then jump into semi-flexible polymers. Okay, so we finish the scattering function. And then first talk about the Kratky model of semi-flexible polymers before going to the warm light chain model, which is also, it's awesome. It's for polymers this week then. Okay, so if we now continue on scattering function, we look at this equation here. That's a sum that one can evaluate. I would suggest that you use tools like Mathematica. Which is actually to say that, I mean, Mathematica is a very useful tool because it's like the best tool that we have for algebraic calculations, and it can happily do these sums. Word of caution, Mathematica at the same time is very bad at sorting terms. So if you have like, you know, an expression that has, I don't know, 4 terms that are proportional to x squared, it will have a hard time to like lump them together and compress the, you know, expression to like something shorthand. So this is typically what you have to do. And also like simple, interestingly enough, they're like functions in mathematics. Okay, so compared to like lots of other like programming languages, I think the biggest drawback of Mathematica is that you somehow have to know the functions that you want to use before you use them. Like you have to know how they're called. So like it's a little like, I mean, if you work with MATLAB or C++ or Python, like you can typically just Google what you want to do, and the web will tell you, okay, this is how you do it, and this is the function that you're going to use. And somehow that doesn't work that well with Mathematica. That you try to say like this is what I want to do, and what's the, I don't know, I want to have a series expansion of, and I don't know, it's very tricky. Anyway, so for this kind of task, like taking sums, it's you just evaluate it. That's easy enough. But then you have to know that, like, for this making terms look nicer, there are actually two functions. So you can have an expression and you say simplify, and then it tries to simplify and sort terms. But then now I have no idea what they thought about it. But then there's another function. It's called full simplify. Interesting. So you have another try of thinking like, okay, let's see how much magic it can do if I do full simplify. And so this is really like, I mean, if you're trying to solve really systems, so like, I mean, this is going to be a closed, nice expression, but in the real world, when you're dealing with a real problem, and you're so happy that there's an analytical expression, but your analytical expression is like a whole page in Mathematica, like continuously, you would so damn hope that it would be better in like sorting terms and making expression looks a little nicer. Anyway, it's yeah. So in this case, it becomes, and it looks like, honestly, like an expression that also, I didn't try to run it on Mathematica myself, but probably it needed some help in sorting terms. It's just, yeah, it's a frustrating bit. But there's no alternative, so it's fast, no worries. And q squared, p squared. Okay, and then another caveat is that, okay, now you have an expression. Hey, you can be proud, it's an analytical expression. But which you can, in principle now, like you can fit to your experimental data, right? That's what it's very useful for. But if you want to gain physical insight of what is actually going on, you would be again interested in taking limits, right? Of saying what happens if I send the bond lengths to 0, and at the same time enlarge these kind of limits. And again, just a word of caution, since I started mumbling about Mathematica. Anyway, that's another thing where Mathematica is bound to fail, and it's down to, and I might have mentioned that before, that you, so doing something like saying, I want to send b to 0 and keep n, and at the same time run n to infinity, the way you plug it in, Mathematica doesn't know that you want to obey both of them at the same time, right? So it will just do it. Like it will just, like if you say I send b to 0, it will just send b to 0, and then subsequently try to send n to infinity, right? Which is not what you meant, and you will get a different result, which you should be puzzled about. And so what you need to do is, again, you need to, and that's why you need these closed expressions of these equations. So what you need to do is, again, find a non-dimensional quantity, n b squared, for example, that you keep fixed, and you run something else to 0. So and b over nbq, like you could consider this one, like this whole expression, right? So you're always looking for these non-dimensional quantities. You replace the terms by this non-dimensional quantity, and then you run this non-dimensional quantity to your desired limits. So this would be the safest part, because it's it's very tricky. And also, I mean, in this expression, it's very clear what's governing the dynamics, right? But in what often happens if you do some calculations, it's actually not easy to identify what are the non-dimensional quantities that are important for your topic, right? Because there might be different choices that are available. And if you don't know yet what you're looking for, you have no idea what is really important. I really remember we had this problem. We wanted to understand if you take your brain, your vessels dilate if your tissue needs more oxygen. And so we described you can fully solve the equations of flow and transport with your blood. And the question was like, how much of a change in molecules that can be absorbed do you get if you just dilate your vessel by a small amount? So you can really fully solve this equation. Nicely works out. You get an analytical expression, which is also more clumsy. But what is actually important, right? So which terms that you can then, if you have multiple of variables popping up, is actually important. I remember like really prodding over this for a week, like a really whole week, just trying to, have these different versions, taking different limits, trying to make sense if I could rationalize the behavior that I would have taking different limits. And so it's not a given. So like if you get stuck on this, and then interestingly enough, I figured out eventually, okay, this is a good choice. And then years later, like really, like it was published and everything, I figured that the dimensionless quantity I'd chosen was actually had a name that was named in the 40s or 50s, the 40s, must have been 40s, by chemists already. So like it was a well-known quantity, but it was really in a very different field where you were dealing with, chemical kinetics. Which I had no idea about, didn't know about, and so, but this was actually quantity, and but these things always happen, by the way. Like it's not. All right. So back to our case. So here in our case, what we see is we find this wonderful big expression, and we may have this impression that this equation is true for all Q, B, and N that we can choose. And thereby, it's important to remind ourselves again that what we put into calculating the scattering function is again the assumption that this is a Gaussian, that we're in the Gaussian limit, and therefore it's not true for all values of Q, but only at length scales much larger than the bond length. And so that's why I will go through the taking limits appropriately to make sure that we're only interpreting what's really physics-based in this mathematical expression. So the formula appears to be valid for all values of Q, which is not true, as still holds. So that means that we only consider length scales that are much bigger than B, which now in Fourier space relates to Q times B being smaller than 1. So I can't resolve below this length scale of a single polymer segment. But it's good to resolve the entire polymer state. And so now expanding for QB smaller than 1, note, non-dimensional parameter, we get then SQ is equal to 1 plus Again, I can identify now NB squared as the end-to-end distance vector scared. This allows me to write this as n squared q over, sorry, q times squared over 6. Oh, no, that's the bracket went too far up. Squared. I'm moving in and then I have a QR squared popping up, sorry, R squared over 3 plus 2 Q squared R squared over 6 minus 1. And that I can identify as n squared. And again, we're back to the bifunction with this being its argument. Sorry, that's a 6. And so now this determines our scattering. So if we actually plot the full function as a function of our wave vector normalized by r squared over 6, it decays from 1 if I also normalize this by n squared. And there are two different regimes, namely for q r squared over 6 smaller, the low scattering factor. This the bifunction becomes n squared 1 minus q squared r squared over 6. So we basically get a scattering function that's really only proportional to the individual scatterers, each having an impact of 1 minus q squared. So this really scatters at low scattering vectors as n individual scatterers coherently, like n scattering centers. And then interestingly, for intermediate vectors, choosing q be between 1 and n squared, square root of n, we get a fractal behavior of the scattering function, namely SQ is equal to this quantity, which means that in this realm, we get the same behavior independent on which scales we're probing the system. So we have a self-similar behavior at the intermediate range. And so here we can't actually resolve that the polymer is built from individual segments. So this is a self-similar on these scales. So I can't observe that the polymer has a finite length, nor that it is built of individual segments. Okay, so this now concludes our journey into flexible polymers. And then the next topic is going to be to look into semi-flexible polymers. So while the flexible polymers, the Gaussian chain, and had given us universal laws on the end-to-end distance, which we also assume because of the central limit theorem to be true if we have local short-range correlations in our polymer. We saw that when we looked at we compared the force extension curve that we predict from the freely jointed chain to the DNA data, there was a significant shift in data. So there's something that we cannot resolve. And so that's why we now turn to build better models, namely semi-flexible polymer. And this will, even though you may not expect this, this will remind you of your models for magnets again. It's just a teaser. Not sure if I actually make it to there today. Ah, well, yeah. Yes, maybe, yes. So remember we had a consistent deviation for the freely jointed chain model to DNA data, and that's saying that, you know, I told you that DNA is the most flexible. Anyway, so we learn from that it's not sufficient to only consider entropic effects. So we need to consider the energy cost of polymer deformation with respect to a ground state. And so in principle, there are two different, where's my beloved cable, two different quantities that we can consider. Namely, one is the bending, which I'm acting against here. Another one is torsion, which is actually not stiffer, if you want to try. Like, this is easier. This is a lot more force for the torsional states. So there's bending and torsion energy to consider. We will actually only deal with the bending energy, but there are, because we here only consider, we continue considering polymers as you know, infinitely thin lines in space, or segments in space. And to consider torsions, you need to also consider that if this were my polymer stretching out infinity, to have torsion, I would need to also take along a vector that lies in this plane and reflects how this is being twisted as we go along. So that's longer, shorter, yeah, like that. And for this, you need ribbon models. So we can, that also exists. I actually worked on it as a student. Yeah, so that would be extensions on it. So to first start with the setup of, you know, how to consider bending energy, let's start with the Kratky Porod model of slash the worm-like chain model is following from it. Okay, so in the Kratky Porod, what we state is that actually if you consider the statistics of now these semi-flexible polymers, there's a typical angle that at which this polymer will be happy to bend. So the setup is that, again, we consider a line of segments and bonds. Numbering them. This is B, length B, this is T1, T2. And now I state that basically the angle between, I just continue this line. I can make this an angle, which I call θ3. And this would then be pi minus θ3. And what I now assume is that this is a fixed angle, and my segment can only rotate around this axis of the prior segment with this fixed angle theta, which I call, this is a bending angle. This is the bending angle. And where am I on this curve? Maybe I should have given it a different color and give me where I'm on this curve. This is my rotation angle. So we're back on having a bead rod chain. And we also consider segments of equal length B. And the state is defined by a set of normalized tangent vectors, Ti, which defines the polymer state. We do neglect any torsion energy. But we consider a bending cost. And so the bending energy cost is proportional to, so there wouldn't be any bending if two subsequent tangents are happily aligned. So the product of Ti, Ti plus 1 is 1. And any deviation from this one is my bending cost. And since I can write this product of normalized tangents also as the angle between them, you can see why this formulation of the bending angle comes into play. So that's the cost associated with different orientations of subsequent segments. And as we're going to see, then we can write this as an elastic energy Hamiltonian. That's for the worm-like chain, just to give this as a heads up, where we have a minus j I going to 1 Ti plus 1, right? If I consider this energy cost and I omit the constant terms, then what's governing the energy is really this product of the two tangents. So here omitting the state independent constant. And if you have a look, that's me advertising that we're back to magnets. That's the same thing as the Heisenberg model, right? So you have a zero applied field. If these are spins in a 1D Heisenberg model. So the spins could take any angle from 0 to 2 pi, and you have a spin-spin interaction. So that's equivalent to the 1D Heisenberg paramagnet nearest. But that's to say that there's going to be, as we're going to see, there's a crucial difference to the Heisenberg model, namely that we, no, that's exactly the same. So the tangents are normalized to 1. That's the inextensibility, but it's exactly the same, except that here we're looking at different quantities of this Hamiltonian. But so while we see this, let's stick with the Krootke-Porot formulation first, where we just merely on stating that we can describe the state of the polymer by the subsequent angles between individual segments, we can learn about the statistics of the system. So let's first evaluate polymer statistics. Oops. Purely based on geometrical considerations. And here it will be useful to consider a fixed bending angle theta. So now the rotation angle is happy to vary between 0 and 2 pi, but we fix the angle between 2 subsequent bonds to theta. So all of them have an angle theta in between them, but are rotated in 3D space. So which is the definition of the Krootke-Porot model. Then we can, the key geometrical property that we're interested in is the tangent-tangent correlation function. Which we define as Cn, which is Ti plus n. Okay, so let's start small. What can we say about 2 neighboring chain segments? Well, we state that Ti plus 1. That's just defined by cos theta I plus 1. Well, but the thetas are all the same. So it's cos theta. But the way I define it here, it's rather than defining it as the angle of theta I plus 1, I define it as the theta I, so pi minus theta. So this is then cos of pi minus theta. I can drop the brackets because the angles are all the same, and that's then minus cos theta. also, just to note, because we're going to use it, if I consider the perpendicular component, the component perpendicular to I plus 1, then because my rotation angle is uniformly distributed between 0 and 2 pi, the perpendicular component of this bond vector takes in opposite values if I take the statistical average, which cancel out. So this perpendicular component, this correlation is actually 0. Where we average over all rotation angles phi in 0 to pi. But this, making note that there's this perpendicular component is the basis to get to this higher order correlation functions. So now let's say I want to have, let me actually denote it, T1 and T3. So the next nearest neighbor correlation function, then I can write this actually as taking the correlation of T1, T2 times T2, because the scalar product of T2 with itself is 1, plus T1, T2, because that correlation is, I'm adding a 0, times T3. And then we can evaluate these individual terms to see that this is T1, T2, and T2, T3, plus now T1, T2, and T2, T3. Now, as we stated up here, this correlation with the perpendicular version, this is 0, same for like the reverse. And these, we also just calculate because these are then the nearest neighbors correlation. So this gives me minus cos, and this gives me another minus cos. Theta minus cos theta. So that in total we have here minus cos theta squared. And so, you know, as we did here for the nearest neighbors, we can obviously keep on doing that. So we can now successively project tangents Ti by writing Ti as a product with this nearest neighbors, and then decomposing its nearest neighbors into its and then adding next nearest neighbors, sorry, Ti plus 1. And then I can write this as its nearest neighbors. So then this becomes Ti plus 1, Ti plus 2. And so on. And so you can see that, you know, we can keep on doing this. And so what it results to is that in the end, I get a decomposition which is the power or to the power of indices I have in between. So therefore, we have that C of n, the correlation function, which is ti plus n, is then minus cos theta to the power of n. And that's the key. Similarly to our endeavors with the flexible polymer, once we have the tangent-tangent correlations as the tangents define the state of the polymer, we can therefrom calculate global quantities, like, for example, the mean square end-to-end distance. So as before, this is just sum over all tangents squared, which obviously is then can write as a double sum I and j, ti, t, j. And that's then either I and j are the same. If I and j are the same, I get a b squared sum I to n t I squared, or I and j are different, and if I and j are different, I can have two versions. I can, for example, have I equal 1 and j equal 2, or can have j equal 1 and I equal 2. So all terms pop up twice. So that gives me a factor of 2 here for each pair of I and j. B squared for the segment length. And then we have here now the ordered sum I going from 1 to until j to n, ti, tj. Now, the correlation function of the tangent with itself, that's just a 1. And so of those, in the sum, we have n of them. So that's b squared n, 2b squared. And then I can rewrite this sum as I going from I from 1 to n and s from I to n minus 1, such that then I have ti plus s. And I rewrote this tangent-tangent correlations in the form of how we know the result, namely as a function of the amount of bonds in between them. And so that we here now know that this is indeed minus cos theta to the power of s. And then we again, just copy this down, bn plus 2b squared. We can evaluate this geometric sum over s. Just copy down the 1 and n. Going to have a lot of geometric sums, by the way, if you want to make yourself familiar with them again. So that's minus cos 2n minus I minus 1 over minus cos theta minus 1. And then also putting those two terms apart, we get, we can take out this term. That's then 2b squared n cos theta over 1 plus cos theta. So I summed up a few minuses. So there's 1 minus here, there's 1 minus there, that makes a plus, and then there's a minus down here, that makes the minus. The sum makes the n, and then we're left with 2b squared and the remaining sum, which is again a geometric. Let me just pull out a few prefactors first. I pull out the prefactors. we get cos theta 1 plus cos theta, and then we have the sum over now minus cos theta n minus I. And then this gives together, actually reformulate this as nb squared that I pull out. 1 minus and reorganizing one more time. Minus, sorry, 2 cos theta over 1 plus cos theta plus 2 plus. Actually, sorry, I think this is. And so, yay, we found an algebraic expression for the end-to-end distance. Note, ta-da, we again found as a prefactor this universal behavior that the end-to-end distance scales with nb squared, though we see there are corrections due to the bending contributions. It's most useful to quantify this property visually by looking at the average projection along, projecting the end-to-end distance along the direction of the first segment. So the idea being that, like, if this is a polymer and I want to know, like, what's the statistic of how long it's been, I fix the polymer in space and take this first direction, and I want to measure, like, where am I ending up here. And the average projection of R along the first tangent T1, sorry, T1 is then looking at R T1. That's much easier because that's then looking at, please not. Yeah, looking at this projection. Okay, so few more lines here missing while the pen is charging. And what we're going to do next is then to see, like, okay, it's useful to use this discretization of a polymer in terms of segments and bonds, because it allows us to really get these analytical results of statistical properties. But we already learned in the flexible polymer case that it was useful to introduce this Gaussian chain, which was coarse graining out the inter bonds distance by coarse graining them into springs. And so in the context of semi-flexible polymer, we will take a continuum limit to now really describe this individual polymers really as a curve in a 3D space that has a bending energy. And this description is the worm-like chain model. And so if we, but for now, just look at Ti projected on T1, that's easier because then we have the distance between I and 1 dominating, which we get the minus cos theta to the power of I minus 1, and is a more closed expression, again, evaluating this geometric sum, theta minus 1, which gives us B1. Oops. And now the continuum limit. Taking the Kratky forward gives us the worm-like chain. And so what we do is, again, we send the segment length to 0 while sending the number of segments to infinity, with now keeping NB fixed, the length of the polymer. Also, we respect that the polymer contour is locally almost straight, which states that this theta is closer to pi. It's closer to pi. And so this now resolves why we here chose, you might have wondered, when starting with the tangent-tangent correlations, we here chose to have to choose the angle of the previous neighbor. So such that here we can now take the angle of theta 2 of theta I being close to pi, so that these are typically straight. And furthermore, we define an important quantity, namely the persistence length, LP, that is equal to B1 plus cos theta. And in this, why this choice? Well, we see this because what we're actually dealing with in all our expressions are minus cos thetas to the power of actually small n for now. And we can write this as expanding it with an exponential ln 1 minus cos theta minus 1. So what I did is I added to this cos theta a minus 1 plus 1, and we put this to the exponent. That's why the n here pops up in front. And we do this because now we can expand the logarithm to get minus nb 1 plus cos theta b, and the, in terms of as deviations from 1, nb squared, no, nb order 2, second order will be, and so on. And then we can approximate, we neglect the higher order terms, we can approximate the tangent-tangent correlations to decay exponentially if we identify LP as the persistence length over which the correlations decay. And this is then exp minus NB over LP, which is nothing else than minus the length of the polymer over the persistence length. And again, we here chose LP such that it's dimension, the length of the dimension of a length, to factor in that what's the intrinsic spatial dimension of the polymer is the length of the polymer, so n times b. And now using this formulation, the projected end-to-end distance vector that already had this b over 1 plus cos theta. Let me just quickly copy it down. So we actually had this structure popping up here, cos theta 1 minus cos theta to the power of n. We can now identify what we have here is a persistence length and 1 minus, and identifying this exactly. And sorry, let me just quickly correct this. So this used to be a big, should be a big capital N. This doesn't make sense. One more. Otherwise, it's not the length. 1 minus E minus L over LP. And so this is a nice example of like, looking at this geometrical relationship for the projected end-to-end distance vector, right? It looked like a horrible expression with lots of cosines in there. But the magic was to identify what is the intrinsic spatial dimension here, such that I can write this as a fraction of spatial dimensions compared to the length of the polymer, which then defines my non-dimensional variable that governs the dynamics of the system, which is here L over LP. And all of a sudden, this, like what looked like a cumbersome expression, simplifies to a very simple expression from which we can read off a lot of insight, right? That if I have a stiffer polymer, the end-to-end distance is much bigger, and the softer it is, the more crumpled up it is. And so this we can now nicely read off, and I hope it also exemplifies that really identifying what intrinsic parameter and in the end non-dimensional variable is governing your behavior can actually take you quite a while if you don't know what you're heading for. Now, having this success, let's also try the even more complex geometrical expression for the squared end-to-end distance vector up here. So let me copy down in terms. So we had b 1 plus cos theta. We had a 1 minus cos theta. We had a 2 cos theta over nb. Another b squared over 1 plus cos theta squared, and 1 minus, sorry, 1 minus missing, minus cos theta to the power of n. And now we can identify all these nice terms that we found. So this is a persistent length. This is a persistent length squared. This is e to the minus L over p. And now we have these two terms that are left. But remember, we said that we're expanding for theta around pi. And so in this limit, theta towards pi, this is roughly 2. And this term is descend theta to pi. This is 2 over L times minus 1. And then just lumping everything together, we find that we have, and this is L, obviously, L again. So only L's and LPs keep popping up, which is really nice. And we find this closed expression for the end-to-end distance vectors, which has a lot of meaning, particularly if we now take the limiting cases to check if this expression actually makes physical sense to us, given our physical intuition of the system. So if we look at for L much bigger than LP, so for a very flexible polymer, we take this limit, we get 2L LP, which is behavior like a freely jointed chain or Gaussian chain. We get an L square for L much smaller than LP, basically for a rod. So how can we make sure that this is our intuition? So obviously, if we have a rod, the end-to-end distance vector should just be the length of the of my rod, which is L, R squared, L squared. Yeah, that's like a rod. And here it's a little more hidden, but if we plug that back in that the length of the polymer is n times the segment distance, that's NB, and that the persistence length is actually, I can interpret this as the coarse-grained length at which the beyond which the polymer can freely bend, then I have a scaling that's proportional to my NB squared, my universal result again. So we can read out an effective Gaussian chain if we identify the, I don't know why I'm calling it A here. Let me change nomenclature to B. B R squared over L equal to LP, which has a name, namely the Kuhn statistical segment. And so we should be very happy to have recovered what we derived previously as a on the use of universal law, because again, we here only consider nearest neighbors energies. And so these are short-range correlations that the system has, so we expect to recover our universal result. Last, then the general tangent correlations. C of S is now the distance between segment I and I plus S, or N, and then taking the limit and N over discretizing N into segment length S by taking B to 0 is minus S over LP. So the persistence length is the characteristic length scale. And so we find an exponential decay of correlations, again, being consistent with our expectation that we have short range correlations. Okay, so this is to motivate that purely the approach by looking at a system on a purely discretized system can be very powerful because have sums that I can evaluate, and really in these limiting cases where I suppose it felt very weird ad hoc to assume that this bending angle is constant, is very meaningful because we already discover closed expressions for the statistical observables. Another approach that's been proven successful is the worm-like chain model. Where we now really start with the Hamiltonian, which sums over the angles, the deviation of the angles from being straight, which is the ground state. And now we want to start with the Hamiltonian and really unfold the power of thermodynamics. So now, like, we're going back to your range of expertise that you should be very comfortable with by now. If I give you a Hamiltonian and I ask you to calculate a partition function free energy and then derive all the properties from there on. But just note that on purely geometrical terms, as you will see, we found the expressions as well. So now I will allow T1, T plus 1 as cos theta I plus 1 to cover where now we consider individual angles theta I. And so if we go back to our toolbox of thermodynamics, we're interested in the partition function, which is summing over all polymer states by looking at integrating over all tangent configurations, e to the k I n minus 1. The choice of nomenclature being on purpose, being beta j, as we had before when we considered Ising models. But no, this is the Heisenberg model, right? Because the tangents take any values between 0 and 2 pi. Any orientation in the unit circle. This to state that this is the integral over the unit sphere. So dt I means that I'm integrating the phi from 0 to pi, and d cos theta I from -1 to 1. And so obviously I can perform this integral over d phi. Okay. Let's go bit by bit. So what you see is that I here chose to define the angle as cos theta I plus 1. So this exponential doesn't actually depend on cos theta 1, like the first angle. And so integrating this one out by taking the integral over the unit sphere gives us a 4 pi. This is the dt1, oh, sorry, T1 integral. And now here taking the, the product now from I equal 2 to n. D phi -1 to 1 d cos theta I. And since I can now write the sum as products, I can, I lump this sum into this product of states. And there's a cos theta I there. Let me change integration constant by denoting cos theta as eta to arrive at the 4 pi. We get 2 pi, and of those, because of this integration of the T1s, integrating them out, we only have n-1 products left. So that's why there's an n-1 here. And now solving the last integral, we arrive. Oh, sorry. We need to expand to make it a sine. Sine h over k. n-1. And as advertised, looking into polymer physics is a nice recap of all lots of concepts that you've seen before. Here the result for the very reminiscent of the Ising model. Now it's very useful to generalize this expression for having individual interaction strength. Why? Well, that's kind of a trick, because what I can then do eventually, if I want to calculate tangent-tangent correlations, is that I can take the derivative of the partition function or the free energy with respect to these individual interaction strengths I to get these TIs down from the exponent. So that's the trick. So generalization to individual interaction strength then gives us for pi. Now I can't write this as exponent, but need to write it as a product starting at 2, sorry, of individual 4 pi sine h ki over ki. And that's useful for the tangent correlation function. Because then if we look at TK, TM correlation, we can write this as, if we just define it as the average of a quantity that we chose to be TK times TM, that's again integrating over all states of the polymer times now plugging in our observable and here generalizing this from I to n plus n minus 1 ki ti plus 1, knowing that we want to evaluate this as all interaction strengths being equal. But this actually allows us to realize that this is nothing but 1 over z of dk minus m z dk k plus 1 dk m. Because that way we get all the tangents in between down. And now taking this derivatives of this partition function with respect to k, we get the sine turns into a cos, cosine. If we take the derivative with respect to the ki and the parabolic cosine. So we get a cotangents term popping up here. And if we take this with respect to this term, constant appears. So that then gives cot k minus 1 over k minus m, which we define to be exp of k minus m b over LP by defining the persistence lengths as LP defined as b over ln cotangents k minus 1 over k. Again, seeking this exponential decay by choosing the appropriate persistent lengths. Well, this looks like a little complicated formula. What does it actually mean? So let's plot this. So if we look at LP over B as a function of K, which is J over KBT, then linear relationship, let me sketch this. Say this would be a linear relationship, then what we observe is that there is at long scales a linear scaling, and only at very small interaction strengths I have this decay to 0. So this persistence length decays to 0 as this approaches 0. This is what we'd expect, right? If there's no energy cost associated with bending, also the persistence length definition becomes obsolete. But this is only true if we really take the temperature to 0 and J equals 0, and it's really finite otherwise. So that's I want to show with this like rapid decay. We comparing to the Kratky porode, we note that both the Kratky porode and the Wormlike chain describe an exponential decay of tangent-tangent correlation. Both Kratky porode and Wormlike chain predict exponential decay of tangent correlations, which means that these correlations are short-ranged with the range being defined by the persistence length. And so we discovered that for LP bigger than L, the length of the polymer, we expect rod-like behavior in ordered state. And for LP smaller than the length of the polymer, our statistics approach a Gaussian chain, which is in a sense a fixed point. If we take the limit LP smaller than L, and but we don't expect any long-ranged order at any finite temperature. So we really close the loop going back to our understanding of spin models, where we don't expect any long-range order to appear in small dimensions, and due to symmetry breaking being small in energetic cost compared to the entropic gain. And indeed, we need to, let me just add this. So there's no phase transition into ordered states here. I.e. to the rod. And so we would expect phase transitions only possible in higher dimensions, and higher dimension version of a polymer is also again of biological importance for membranes. So like the membrane housing, your cell is also a semi-flexible entity because it's built of individual, like if this is the membrane, it's a sheet of polymers. And so if you want to bend them, these individual polymers would come in close contact. There's steric and also charge repulsion. So there's a bending energy. And indeed, in this context, you can have phase transitions. And for example, the best model of where really the membrane is fully capturing the physics of a cell are your red blood cells. So your red blood cells are basically a semi-flexible sheet. In this context, really, you can have diseases that are associated with the phase transition of your red blood cell membrane, which turn out to be a disease because actually your red blood cells have to be very, very squishy to actually fit through these tiny capillaries to perfuse your entire body with glucose and oxygen. And it doesn't do such a good job if the membrane is stiffer and they can't squeeze. But this just as an outlook that indeed this whole plethora of looking at phase transition really nicely maps in this context here. And we continue on the continuous form-like change chain model next week. And thank you for your attention.